To increase the performance of my Stirling engine, I need high pressure resistant 3D printed parts for the thermoacoustic gas cycle. I printed many samples from different types of filament to test them with up to 12 bar air pressure. In my previous video, I already checked conventional materials such as PETG and ASA. Now I'm trying out the carbon fiber reinforced engineering filaments PA12CF, PCPBT-CF and ASA-CF and would like to find out if they give better results in the pressure tests. In order for the thermoacoustic Stirling engine to seriously produce energy to support our solar plant, its power must be significantly increased. I would like to achieve this by optimizing the thermoacoustic gas cycle, pressure charging and the use of other working gases such as helium, among other things. 3D printing enables rapid prototyping of even the most complex components, which allows for fast development of the engine. I have optimized my print settings and treatment with Dictol, enabling me to reliably print pressure-tight parts using conventional materials such as PETG or ASA. With a wall thickness of 4 mm, these can withstand pressures of up to 10 bar. I received several rolls of fiber reinforced engineering filaments from extruder to test and immediately printed many samples, which now have to prove if they are superior to conventional printing materials. First, here are the results for the conventional unreinforced filaments once again. With only one wall layer and a material thickness of 2 mm, I had major tightness issues with PETG and the layer adhesion failed at 3 bar. ASA exploded spectacularly at 4 bar and PLA burst at 8 bar, causing the filament itself to tear. With 4 wall layers and a material thickness of 3 mm, ASA exploded at 8 bar and with 10% overextrusion at 10 bar. PETG leaked at 11 bar or burst into many small shards. Now it's time for the carbon fiber reinforced engineering filaments with 3 wall layers and a material thickness of 2 mm. ASA-CF exploded cleanly between the layers at 11.5 bar. PCPBT-CF remains completely leak-proof up to a maximum pressure of 12 bar. PA12CF can also withstand overpressure of up to 12 bar without problems. Unfortunately, I'm unable to achieve pressures higher than 12 bar, which would give even more meaningful results. Overall, carbon fiber reinforced engineering filaments show higher compressive strength with thinner wall thicknesses, which is probably mainly due to better layer adhesion. So, I will probably manufacture my high-pressure components for the thermoacoustic Stirling engine from carbon fiber reinforced PA12 or PCPBT. These materials have made the best impression for me and achieved the best results in the pressure tests. Many have reported problems with water absorption and brittleness in the long-term usage of untreated PA printed parts. My tests will also provide insight into their long-term suitability. I'm curious to see how sealing with Dictol will prevent long-term problems with printed nylon. Now I'm going to print some components for the Stirling engine and hopefully report back soon with successful results. As always, I look forward to your comments on Discord or here on YouTube. Thanks for watching.